Hello, and this is just a short one about the oxygen cycle. And if you remember back to the last video, remember in the last video we were talking about temperature proxies. I mentioned that one of the ways that you could tell the difference between shells of forams and diatoms created and grown during in cold climates versus hot climates is the isotopic content of them, and specifically the isotopic content of oxygen within the calcium carbonate shells and silicon dioxide shells of the forams and diatoms respectively. So this one slide, a couple of pictures here, shows us why it is that we can correlate the isotopic content of oxygen within these shells and various other things, as it turns out, with the temperature. So, first off, there are two common isotopes of oxygen. It's actually three, though the third is less common than anyway, two. We'll go with two. There are more, though, just to be technically correct. And oxygen-16 is by far the most common one. It is stable, does not go through radioactive decay, and it comprises about 99.8% of all oxygen nuclei. Now, the next most common isotope is oxygen-18. So it has two more neutrons in it than the oxygen-16. And that makes it just a little bit heavier, gives it a little bit more mass. And as it turns out, that gives it slightly different properties when it comes to evaporation and condensation. So you see in the diagram here, let me grab my pen. You see down at the equator, or nearer the equator, it says you have water, slightly depleted in oxygen-18, evaporates from warm subtropical waters. Okay, so what that is telling us is that it's slightly depleted. And why is that? Well, oxygen-16, because it is lighter, evaporates a little more readily than oxygen-18. So if you just look at the waters themselves, well, then it's, the normal proportion. But as things evaporate and you get that into the water vapor within the air, well, that's going to be richer in oxygen-16 because oxygen-16 evaporates a little more readily than oxygen-18. And because of the circulation of air within the atmosphere, that air then travels northward on average, and so you see that in this arc going up here in this picture. And you have the oxygen-18 stuff, right? Oxygen-18 being heavier, it condenses more readily than oxygen-16. So the oxygen-18 it does evaporate and goes up into the air and water vapor, condenses out, rains out back into the oceans and over the continents as it's heading up the globe, as it's heading up in latitude. And once you get near the poles, well, a whole bunch of the oxygen-18, right, has condensed out and fallen as rain. And so you're increasingly depleted in terms of oxygen-18. And when it finally comes down as snow and then gets packed into ice here at the poles, well, you have about 5% less oxygen-18 compared to sort of your average bit of ocean water. And then whenever that snow and ice melts, well, then the water there, before it then circulates and everything like that, but the meltwater, when things are melting in Antarctica, for instance, that is going to be depleted in oxygen-18 as well, because it has 5% less here in the ice, then the meltwater that it creates is also going to be depleted in oxygen 18. Now, the fact that you have oxygen 18 condensing a little more readily and oxygen 16 evaporating a little more readily, and you have this cycle of the water evaporating and then rising up into the atmosphere and then precipitating out and all that kind of thing that we just went through, well, that allows you to correlate the level of oxygen 18, that rarer isotope, with the temperature at which the ice was created, or in the case of the shells of the forams and diatoms, the temperature of the water around these things when they were created. Okay? And over here in the graph, they've taken data to support this. You've got oxygen 18. Okay? So it's not the straight percentage because there's only 0.2% of it overall out of all the oxygen nuclei. But this is the delta. That's why the little Greek symbol here in the percentage. Okay? So if 0.2 was 100% of the normal, then you have less or more based on this. You can see that if you sample up here at sort of warm temperatures, so this is like 25, 30 degrees C, then you have pretty much the normal proportion of oxygen 18, right? 0% delta from the normal proportion of it. But as you go down in temperature, the amount of oxygen 18 decreases until when you're talking about the coldest spots, Greenland, Antarctica, a few other bits and pieces around the globe, you're talking at about, maybe 5%, so less, so -5 meaning 5% less oxygen 18 in that ice and snow and meltwater than you would otherwise have. And so the temperature correlates very closely with this decrease in the amount of oxygen 18. And by sampling the amount of oxygen 18 incorporated within the shells of those forams and diatoms, and also the amount of oxygen 18, for instance, in the ice cores that you read about for this class, they can correlate that with the temperature at which the ice or shells or whatever else was created. And it's a very clever workaround to reconstruct the temperature history of Earth through these proxies. So we'll end this here, and we'll pick up with sort of our summary of these factors with climate change and talk a little bit about the effects of climate change in the next videos.